Welcome back, everybody. We are now going to proceed to a new section, which is multiple regression analysis, the problem of estimation. So far, whatever we have discussed relates to a two-variable regression analysis model, right? A multiple regression analysis means that there are more than one explanatory variable. Or there are more than two variables in this model. Remember, first variable that we are counting is always the dependent variable y. In the two variable regression model, we had y and we had one x or independent or explanatory variable. So in a multiple regression model, you will have more than two variables, which means one dependent variable y and more than one explanatory variables or more than one x variables. So the simplest multiple regression model would be a three variable regression model. What are the three variables? Y and your two explanatory variables, which we are naming x2 and x3. So what will your population regression function look like? It will look like equation 1, which is yi is equal to beta 1 plus beta 2 x2I plus beta 3 x3I plus ui. The interpretation of this model remains the same. Yi are the different observed dependent variables. x2I is the different x2 variables, different levels of x2 variables. x3I will be different levels of x3 variable, right? ui is again the deviation between the observed yi minus the estimated yi hat, right? This is still called the error term, the disturbance term, the deviation between observed and estimated value. Beta 1, beta 2 and beta 3 are called your regression coefficients, partial regression coefficients. Here beta 1 is the intercept term. Remember, intercept term means the point where the regression line will cut through the y-axis, or that is in the two variable case. In a multivariable case, the intercept term means the value, average value of y when all the x variables are assumed to be 0. So it is the average effect on y when all the other x variables are excluded from the model. By excluding, all I mean is I will set all the x variables, whether it's x2, x3, x4, I'll set them all equal to 0. So I will have the mean value or mean average effect on y. Beta 2 and beta 3 are called the partial regression coefficients. Now, when you have shifted to a multivariable model, or in our case, we are discussing the three variable regression model, we continue with the assumptions of CLRM. If you remember, when it was a two variable case, we had 7 CLRM assumptions. We continue with the same assumptions, okay? But 2 more additional assumptions are being made. I'm calling it assumption 8 and 9 because assumption 1 to 7 are the same as what we have discussed earlier. What is assumption number 8? It says that we assume that there is no exact collinearity between the explanatory variables. Technically, it is called the assumption of no multicollinearity. So it means that we assume that there is no exact linear relationship between variable x2 and variable x3. We shall discuss the technical facets of this assumption later on, but intuitively, if we are saying that x2 and x3 have some sort of an exact linear relationship, by linear relationship I mean something like, let me show you what I mean. Suppose we have a linear relationship between x2 and x3. I'm saying x2, sorry, I'm saying x2 is say equals to 2 times x3. Now if this is an exact linear relationship, because x2 can be expressed as a linear function of x3, right? So if this relationship is valid, then my original PRF is yi equals to beta 1 plus beta 2 x2I plus beta 3 x3I plus ui, right? This was my PRF function. Again, I am discussing a 3-variable regression model here. Now, if I know that x2 is equal to 2 times x3, I can write, instead of x2, I am going to write it as 2 times x3I plus beta 3 x3I plus ui. So now I can take x3I common. So I have got 2 beta 2 plus beta 3 in my brackets plus ui. Now if I assume this to be some coefficient alpha, I can write this as yi is equal to beta 1 plus alpha times x3I plus ui. So this equation, this was my first equation, population regression function. Now the second equation has been derived based on the fact that x2 and x3 have an exact linear relationship. x2 is equal to twice x3. Now if you put that into my PRF function equation 1, what I get is, in effect, I have reduced my regression model into a 2-variable regression model, where if I try and estimate using OLS, I will be able to estimate a parameter beta 1 and estimate and arrive at an estimator for alpha, right? We know that alpha is equal to 2 beta 2 plus beta 3, but we will be unable to distinguish between how much or what is the effect of x2 individually on yi and what is the effect of x3 individually on yi. This becomes impossible because both x2 and x3 are amongst themselves linearly related. When we try to estimate this regression, all we will be able to arrive at is a value for alpha, which measures the combined influence of x2 and x3 via variable x3 on y. So the intuitive logic behind the assumption of no multicollinearity is that if there is an exact linear relationship between the explanatory variables, to find an individual influence of each explanatory variable on y will be near impossible, right? So in case while you're doing your research you do find 2 variables which are exactly collinear or exactly linearly related, it will make more sense to put in any one of these variables and estimate the effect of the combined influence of these variables via the chosen single explanatory variable. Our ninth assumption that we have included is that there is no specification bias, which means that we have correctly specified the model. Okay, once again we are assuming away any errors in determining the model. Now, what is the interpretation of this model? It remains the same as a two variable case, that is given the assumptions of CLRM. If we are taking conditional expectation on both sides, our population regression function or our population regression line is the conditional expectation line. It gives you the conditional mean or the expected value of y given the fixed values of x2 and x3. This is very similar, very analogous to how we had translated or interpreted the population regression function in the two variable case. There also we said it was the conditional mean of y given the value of x. Here we are saying conditional mean of y given the values of all x values, all x variables, x2, x3, if we have more than that, x4, x5 up till xk. We are still interpreting the population regression function as the conditional mean of y conditional upon fixed values of the x variables. Remember, beta 2 and beta 3 are called the partial regression coefficient. So beta 2, when we say it is the partial regression coefficient of variable x2, it means that it measures change in the mean value of y for a unit change in value of x2, holding all the remaining x variables constant. Similarly, partial regression coefficient beta 3 will measure the change in the mean value of y or change in E of y for a unit change in x3, keeping all other x variables constant. When you listen to this, just recall how I used to explain to you what partial differentiation means. When you're doing partial differentiation with respect to any one independent variable, we are assuming all other independent variables to remain constant, right? Similarly, it's the same logic that we are using over here. We are saying that beta 2 measures change in y due to a unit change in x2, holding variables x3, x4, x5, etc. constant. So another way of saying it is the net effect of a unit change of x2 on the mean value of y. Now, if the PRF has a structure like that, the first equation here gives you the sample regression function. How will it look like? What will it look like? yi is equal to beta 1 hat plus beta 2 hat x2i plus beta 3 hat x3i plus ui hat. Okay, it is exactly the same as what we were discussing in two variable model. Only here we have additional explanatory variables, so we have an additional estimator. So beta 1 hat is an estimator of the true population beta 1. Beta 2 hat is the estimator for true population beta 2. Beta 3 hat is the estimator for the true population beta 3. And ui hat is the estimator for the error term ui in the PRF or the population regression function. Once again, our criteria for estimating remains the ordinary least squares. That is the one that we are discussing. Remember, this criteria is to ensure that the SRF that has been estimated is as close as possible to the true PRF or the population regression function. So we are still minimizing ui square or the deviation squared. Okay, I'm sorry for a small misprint. Just minimize ui hat square. 1 second. Okay, we are minimizing ui hat squared, which will be given, which will be expanded as summation of yi minus beta 1 hat minus beta 2 hat x2i minus beta 3 hat x3i, the whole squared. Okay, since we have three variables in this model, y, x2, x3, when you do the differentiation, you will have three first order conditions, and from these three first order conditions you will get three normal equations, right? So if you're generalizing it further to a k variable regression model, depending on the number of variables in your model, you will have that many normal equations. Here I have just copied down the normal equations. The first normal equation is always based on the means. Y bar, or mean value of y, is equal to beta 1 hat plus beta 2 hat x2 bar, that is mean value of x2, plus beta 3 hat x3 bar, that is the mean value of x3 from the sample that is given to you. My second normal equation will be summation of yi with the second variable x2i. The third normal equation will be summation of yi multiplied by the third variable x3i. Okay, I have just listed these. Just understand the logic of these normal equations, how the normal equations are formed. You don't need to by heart the formulas of beta 2 hat and beta 3 hat. Once again, the derivation you have understood from the two variable model. It is along the same lines, except the derivations for these three variable and higher variable cases are more easily done using matrices. Okay, to show them, but since the proofs are not important for you, I have just listed down the formulas here. The intuitive logic remains the same as in the case of a two variable case. Okay, in this slide I have listed down the variances and the standard errors. Remember, standard error is always square root, the positive square root of the variance, and the variance of beta 1, variance of beta 2, as well as variance of beta 3 have been noted down over here. If you notice, the variance of beta 2 can be written in two ways. One is this, and in the second one, instead of the denominator, the this part can be simplified by using the term R23. What is R23? It is the correlation coefficient between x2 and x3. Okay. So this formula which is written second is often easier to remember. Similarly, variance of beta 3 can also be written in two forms. One is this, and the other is again when we are replacing this fraction using the coefficient of correlation variable. So this is always the sample coefficient of correlation between x2 and x3. The final equation over here, the final formula over here gives you the covariance between beta 2 hat and beta 3 hat. That is the two estimators. although these formulas look very big, if you compare the variance of beta 2 and variance of beta 3, they are very symmetric. So you just have to look at symmetric. The numerator is the only thing that changes. The denominator remains the same. Okay. Again, when you're looking at it in terms of using R23, the term outside, when you're using the correlation coefficient, if you're looking at variance of beta 2, over here it will be summation x2i whole square, and if you're looking at variance of beta 3 in terms of the correlation coefficient, here the denominator, the term will be x3i whole square, summation x3i whole square. Right, just have a look. There is no need to remember the proofs for the 3 variable part model. Okay, and also since the population sigma square is not known to us, we need to know its unbiased estimator, which is sigma hat square is summation ui hat square divided by n minus 3. Remember, n minus 3 is the degrees of freedom of the model. Since we are estimating 3 estimates, that is, we are estimating beta 1 hat, beta 2 hat and beta 3 hat, we lose 3 degrees of freedom, and that is why it is divided by n minus 3. Your sigma hat square or your sample variance is summation ui hat square divided by n minus 3. The minus 3 comes from the fact that we are losing 3 degrees of freedom because we are estimating 3 estimators. So if you have a k variable model, your sigma hat square will be summation ui hat square divided by n minus k, right? 3 variable model, it is n minus 3. Earlier what we had discussed was a 2 variable model, so it was n minus 2. In general terms, for a k variable model, regression model, your unbiased estimator for population sigma square will be sigma hat square, and the formula will be this. Another way of calculating summation ui hat square is given in the second equation. Once again, if you have to generalize it to a k variable case, you will be adding a few more terms such as minus beta 4 hat summation yi x 4i and so on till minus beta k hat summation yi x ki and so on.